Module 8, Lecture B, Responsible Model Use. By the end of this lecture, you will be able to interpret model behavior using coefficients, rules, errors, plots, and feature sensitivity checks. Evaluate practical limitations such as overfitting, imbalance, bias, data drift, and explainability. And communicate a complete mechanical engineering AI project with evidence-based recommendations. Model interpretation. Coefficient interpretation. Model coefficients help explain how each input feature is linked to a prediction when other inputs are held constant. In an engineering model, a positive coefficient suggests that increasing an input raises the predicted outcome, while a negative coefficient suggests it lowers it. This can make a model easier to interpret, but coefficients should be treated as patterns based on the data and model assumptions, not as universal truths. When interpreting model coefficients, consider both sign and size. The sign shows whether a feature is linked to an increase or decrease in the outcome, while the size suggests strength only when features are on comparable scales. Scale matters because a small coefficient can still have a large effect if the feature changes in tiny units. In a machinery maintenance model, positive coefficients for vibration or lubricant age may indicate higher wear risk, while a weak or unexpected temperature effect should be examined rather than ignored. When interpreting coefficients, always consider the model context, data quality, and the difference between correlation and causation. A coefficient may show that a feature helps predict an outcome, but it does not prove that changing the feature will change the result. Coefficients are most useful when combined with domain knowledge, residual analysis, and sensitivity checks, so teams can reason carefully and explain model behavior clearly. Python code coefficient interpretation. Coefficients show how features relate to predicted engineering outcomes. Scaling makes their sizes easier to compare fairly, while sensitivity checks reveal how predictions change in practical terms. We import 3 core Python libraries for data work: NumPy for efficient numerical calculations, Pandas for organizing and analyzing data in tables, and Matplotlib PyPlot for creating visualizations to help interpret results. A reproducible pump operations dataset is created by using a fixed random seed and generating 40 flow rate values. The flow rates are uniformly sampled between 80 and 220 gallons per minute, giving a consistent dataset for later analysis. The data is simulated by generating 40 pump efficiency values between 0.68 and 0.92, along with pressure values from 35 to 95 pounds per square inch. Random noise with an average of 0 and a standard deviation of 1.8 is added to represent real-world variation and measurement error. Energy in kilowatts is estimated from a base value, then adjusted for operating conditions. Higher flow rate and pressure increase the energy estimate, while higher efficiency reduces it. A small amount of noise is added to reflect real-world variability. We use Pandas to create a data frame that organizes the generated data into a structured table. It includes flow rate, pressure, efficiency, and energy, making the data easier to manage, analyze, and work with. The code first confirms that the dataset has 40 rows and 4 columns, matching the expected structure. It then checks for missing values to ensure the data is complete and reliable for later analysis or model training. We prepare the data by selecting flow, pressure, and efficiency as the input features used to predict energy consumption. These feature values, along with the energy consumption target values, are converted into NumPy arrays for efficient numerical analysis. This creates the basic structure needed for later steps, such as standardization and regression modeling. To standardize the dataset, we first find the average value of each feature and use it to center the data. We then calculate each feature's population standard deviation to measure its spread. Finally, we subtract the mean and divide by the standard deviation, giving each feature a mean of 0 and a standard deviation of 1, so regression coefficients can be compared more fairly. To set up linear regression, we add a column of 1s to represent the intercept, then combine it with the scaled features to form the design matrix. We then use NumPy's least squares function to find the coefficients that best match the features to the target energy values. These coefficients include both the intercept and the feature slopes. A data frame is used to present model coefficients in a clear table. It pairs each feature name, including the intercept, with its corresponding coefficient. The coefficients are rounded to 3 decimal places for readability, then converted into a pandas data frame for easy display and interpretation. The output introduces the standardized linear coefficients for the pump energy model and presents them in a clear coefficient table. It explains that positive coefficients mean a feature increases predicted energy when other factors stay constant. The negative coefficient for efficiency matches engineering expectations, since higher efficiency should reduce energy use. First, we define a baseline by taking the average value of each feature across the dataset. Then we compare 2 scenarios where only the flow rate changes, one lower by 1 standard deviation and one higher by 1 standard deviation. This isolates the effect of flow rate on predicted energy output while keeping all other features constant. To predict energy for lower and higher flow scenarios, combine the baseline and adjusted flow cases, then standardize each feature using its mean and standard deviation. Add an intercept term for the linear model, and use the regression coefficients to compute the predicted energy values for each scenario. The code measures how much the model's predicted energy changes when flow rate increases by 1 standard deviation, with other features held constant. It does this by comparing 2 predictions and then prints the energy change rounded to 2 decimal places, giving a simple measure of the model's sensitivity to flow rate. The plot summarizes how each feature affects the pump energy model by showing standardized coefficients as bars. Positive coefficients are colored steel blue, while negative coefficients are colored tomato red, making the direction of each effect easy to see. A 0 reference line separates positive and negative values, and the labeled axes and title clarify that the chart is used to interpret the model's coefficients. This script uses linear regression to estimate how pump flow rate, efficiency, and pressure affect energy consumption. It creates synthetic data, standardizes the features, and fits the model using a least squares method so the coefficients can be compared fairly. The results show the direction and strength of each factor, including a sensitivity check for how a 1 standard deviation increase in flow rate changes energy use. A coefficient plot summarizes the findings, with positive values increasing energy consumption and the negative efficiency coefficient matching engineering expectations. Rule-based insights. Rule-based insights make model behavior easier to understand by turning predictions into clear conditions or thresholds. In mechanical engineering, this can show why a model predicts pump failure risk or rejects a part based on factors such as vibration, temperature, operating hours, surface roughness, or cutting speed. By linking outputs to physical reasoning, rule-based interpretation helps engineers check that model decisions match the processes being studied, rather than treating the model as a black box. Rule-based insights connect machine learning results with domain expertise by making model decisions easier to understand. Methods such as decision trees and rule learners can explain classifications, and even complex models can be summarized with simple rules for engineers and managers. These rules do not prove universal truths, but they provide useful starting points for checking model behavior against real system data. Rule-based insights should be treated as useful but limited hypotheses, not automatic instructions. Even clear rules can hide uncertainty and may only work under certain equipment or conditions. In AI projects, explain what a rule means, how reliable it is, and check it with error analysis and engineering judgment before using it for decisions. Python code. Rule-based insights. Rule insights make model predictions easier to inspect by turning them into practical engineering conditions. In this example, simple pump maintenance thresholds are compared with observed failure outcomes. The script imports 3 key Python libraries for data work. NumPy supports efficient numerical operations. Pandas helps manage and analyze structured data. And matplotlib/pyplot is used to create visualizations. Together, these tools prepare the script for data processing, analysis, and plotting. We create a small, deterministic pandas dataset to represent pump maintenance data. It includes vibration level, temperature, service hours, and a failure indicator showing whether each pump failed. This simple structure supports basic analysis of maintenance conditions and failure outcomes. We first check that the dataset includes the required fields for vibration, temperature, operating hours, and failure status. If any field is missing, the validation reports which one is absent. We also confirm that the dataset has at least 4 records, ensuring there is enough data for the rules to be applied meaningfully. Pump maintenance risk is assessed using 3 engineering thresholds: vibration at or above 5.5 millimeters per second, temperature at or above 80 degrees Celsius, and service time of at least 2,500 hours. Pumps meeting these conditions may be at higher risk of failure and should be flagged for maintenance attention. A new risk indicator is created for each pump by checking whether vibration, temperature, and service time all exceed their thresholds. If all 3 conditions are met, the pump is marked as high risk. This true or false result is then converted into a numeric prediction, where true becomes 1 and false becomes 0, so it can be compared with actual failure data. The code evaluates a failure prediction rule by comparing its predictions with the actual outcomes and calculating the share that are correct. It also counts how many pumps the rule labels as high risk, showing both the rule's accuracy and how many pumps it identifies as potentially problematic. The rule identifies pumps as high risk when vibration, temperature, and service time are all high. Its performance is summarized by how many pumps it flags and by its accuracy against observed failures in the small dataset. The main takeaway is that the rule is easy to understand, but it needs more validation before being trusted in broader use. Each data point is styled to compare the rule's risk prediction with the pump's actual outcome. Points predicted as high risk are colored crimson, while others are steel blue, and actual failures are marked with an X, while non-failures use circles. A plot is then created to make these prediction and failure patterns easy to compare visually. The pump data is plotted 1 row at a time, with vibration amplitude on the horizontal axis and bearing temperature on the vertical axis. Each point's color shows whether the rule marked the pump as high risk, while its marker shape distinguishes failed pumps from the others. The points are made large enough to be easy to see. The plot is annotated with threshold lines for the rule. vibration amplitude at 5.5 millimeters per second, and bearing temperature at 80 degrees Celsius. The axes are labeled to show vibration and temperature, and the title identifies the chart as a rule-based view of pump failure risk. After adjusting the layout, the plot is displayed so the rule can be visually compared with observed pump failures. This script tests a simple rule for predicting pump failure from a small dataset. It marks a pump as high risk only when vibration, temperature, and service hours are all above set thresholds, then compares those predictions with actual failures to calculate accuracy. It also reports how many pumps were flagged and visualizes the results with threshold markers. The rule is easy to understand, but the results need validation on broader data before it can be considered reliable. Error pattern analysis. Error pattern analysis looks past overall accuracy to find where and why a model fails. In engineering, this can reveal hidden weaknesses, such as missed early failures or confusion caused by changing conditions. Studying these mistakes helps explain what the model has learned, where it needs better data or features, and when human oversight is still needed. Analyze model errors by grouping mistakes according to the conditions in which they occur. For classification, distinguish false alarms from missed detections because they have different consequences. For regression, look for situations where predictions are consistently too high or too low, which may reveal missing features or gaps in training data. Visual tools such as residual plots can help reveal patterns, but engineering judgment is needed to interpret them and guide model improvement. Error pattern analysis connects a model's technical performance to the real decisions it supports. In mechanical engineering, the seriousness of an error depends on context, such as whether it affects a low-risk estimate or a critical stress prediction. By examining when and why errors occur, engineers can judge whether a model is reliable, needs retraining, or should only support human decisions. This helps students clearly explain model limits and decide when a model can be trusted or should be redesigned. Python code, error pattern analysis. Analyze model errors under different operating conditions using synthetic pump vibration data. Focus on comparing residuals across speed ranges to see where the model performs well and where its errors increase. We import NumPy for numerical work and random number generation, Pandas for organizing and analyzing data in data frames, and Matplotlib's plotting tools for creating charts and visualizations. We set a fixed random seed with NumPy, so random results stay the same each time the code runs. This makes experiments reproducible and helps with debugging. The setup creates 80 simulated pump operating conditions for later vibration analysis. It generates random pump speeds between 900 and 3600 revolutions per minute, along with random load percentages between 30 and 95. Together, these values represent a range of possible pump speeds and loads. To simulate true vibration in millimeters, random noise is generated with an average of 0 and a standard deviation of 0.18. The vibration value is then modeled as a linear combination of speed and load, with speed multiplied by 0.002 and load by 0.018, plus the noise. This captures how operating conditions affect vibration while adding realistic random variation. This simulates a biased model for predicting vibration from speed and load percent. The prediction combines speed multiplied by 0.0017, load percent multiplied by 0.02, and a constant bias of 0.35. Because the model is intentionally imperfect, it can be used to study prediction errors. We use a Pandas data frame to store the pump data in a structured way, including pump speed, load percentage, actual vibration, and model predicted vibration. This makes it easier to analyze the data, calculate errors, and compare predictions with real measurements. The code first finds the residuals by comparing actual vibration values with the model's predictions, showing whether the model predicted too high or too low. It then takes the absolute value of those errors to measure their size without considering direction. This helps evaluate the model's overall accuracy. The code validates the data by checking that the data frame has the expected number of entries and that none of its values are missing. This helps confirm the dataset is complete and reliable before any analysis is performed. To analyze how errors change with pump speed, the data is grouped into low, medium, and high speed ranges. A pandas binning function creates a new speed group column, assigning speeds from 0 to 1800 as low, 1800 to 2700 as medium, and 2700 to 4000 as high. This makes it easier to compare errors across different speed levels. The data is grouped by pump speed category, such as low, medium, and high, so model errors can be compared across operating conditions. For each group, we calculate the average residual, the mean absolute error, and the number of cases. This shows both the direction and size of prediction errors, as well as how much data supports each speed category. To find the weakest operating region, identify the speed group with the highest average absolute error. Then retrieve that error value to see how large the prediction error is. This shows where the model is least accurate and helps pinpoint the speed range that needs the most attention. The analysis summarizes error patterns in a pump vibration model by reporting rounded error statistics and identifying the speed group with the highest average error. It also gives that group's mean absolute error to 3 decimal places. A positive residual means the model predicted vibration too low, helping interpret where the model is underperforming. This plot checks whether prediction errors are related to pump speed. It shows residuals, meaning actual vibration, minus predicted vibration against pump speed, with a horizontal zero line to separate positive and negative errors. Semi-transparent points help reveal overlap, while clear access labels and a title make the purpose of the residual plot easy to interpret. This script evaluates a pump vibration model by comparing synthetic true vibration values with biased predictions. It focuses on residuals, or the differences between actual and predicted values, grouped into low, medium, and high speed ranges. By calculating average residuals and absolute errors, it identifies the speed range where the model performs worst. Positive residuals mean the model is underpredicting, and a scatter plot of residuals against speed helps reveal speed-related error patterns. Practical model risks. Data drift. Data drift occurs when real-world data after deployment no longer matches the data a model was trained on. This can happen as equipment ages, sensors are recalibrated, materials change, or seasons shift. As conditions change, a model that once performed well may become less reliable, even while still producing confident predictions. Data drift can affect both model inputs and what the target outcome means. Input drift occurs when feature patterns change, while concept drift occurs when the link between features and outcomes changes. In mechanical engineering, this matters because a model can fail even when simple accuracy checks do not reveal the problem. For this reason, models need ongoing monitoring after deployment, not just one-time validation. Managing data drift means treating a model as part of a changing system, not a fixed product. Teams should compare new data with training data, track performance, and investigate unusual shifts before relying on the model for important decisions. Retraining may help, but the real issue could be changed data collection, sensor calibration, or operating conditions. Because drift affects safety, cost, and reliability, it is an engineering governance concern, not just a statistical one. Python code. Data drift. Data drift can reduce the accuracy of engineering models after deployment. This example compares development data with operating data and uses a simple rule to show how prediction error can change over time. We begin by importing two key libraries: NumPy for efficient numerical work with arrays and calculations, and Matplotlib's plotting tools for creating visualizations. Together, they help us analyze data and spot trends such as drift in engineering models. A fixed random seed of 42 is used, so the generated numbers are the same each time, making the example repeatable for testing and debugging. The simulation uses 80 samples, and a check confirms this is more than 20 to ensure there is enough data for meaningful analysis. The development data is simulated by generating vibration values in inches per second from a normal distribution centered at 0.18, with modest variation. Random noise is also generated from a normal distribution centered at 0 to represent real-world uncertainty. The remaining useful life is then estimated by starting from 120, reducing it based on vibration, and adding the noise. So higher vibration generally leads to shorter equipment life. To model a later operating phase with more wear, random vibration values are generated around 0.26, with added random noise centered at 0. The remaining useful life is then estimated by reducing 120, based on 310 times the vibration level, and adding the noise. This captures the idea that higher vibration lowers the predicted lifespan of the equipment. To build the linear regression model, we first find the average vibration and average remaining useful life in the development data. Then use these values to center the data. The slope is calculated by comparing how vibration and remaining useful life vary together, then dividing that by how much vibration varies on its own. This slope shows how much the predicted remaining useful life changes for each unit increase in vibration. We first find the intercept of the linear model by using the average remaining useful life, the slope, and the average vibration value. This intercept sets where the model line crosses the vertical axis. We then use the slope and intercept to predict remaining useful life for both the development vibration data and the operational vibration data, so the model's performance can be compared on familiar data and new data. We compare model accuracy by calculating the mean absolute error for both development data and operational data. We also measure data drift by comparing the average vibration in operation with the average vibration during development. Finally, we divide the operational error by the development error, using a small safeguard to avoid division by 0 to show how much prediction error has increased as the input data shifted. The output compares vibration and prediction error between development and operation. It reports the average vibration in each phase, then calculates the drift as the difference between them to show how the input data has shifted. It also compares the mean absolute error in both phases and reports an error increase factor, showing how much prediction accuracy worsened during operation due to data drift. Create a 7 by 4 inch plot and overlay 2 histograms to compare vibration data from development and operation. Both use 12 bins and semi-transparent bars with labels to distinguish the two phases. This makes it easier to see differences in their distributions and monitor possible shifts or drift over time. The plot is labeled to make the comparison clear. The horizontal axis shows pump vibration in inches per second, and the vertical axis shows the number of observations. Its title highlights the key finding that operating vibration has shifted upward, indicating data drift from the development data. A legend distinguishes the development and operating distributions, so the change is easier to interpret. Matplotlib adjusts the plot layout so all elements fit cleanly within the figure. The tight layout function handles spacing automatically, and the show function then displays the plot so you can inspect data drift between development and operating conditions. This script shows data drift by comparing machine vibration data from model development with data collected during operation. A linear model trained on the development data predicts remaining useful life from vibration, but operational wear raises vibration levels and shifts the data distribution. As a result, prediction error increases noticeably on the operational data. Histograms and mean absolute error together show why deployed models need ongoing drift monitoring. Bias and imbalance. Bias and imbalance happen when training data does not represent the full range of situations a model will face. In mechanical engineering, data may come from limited machines or operating conditions, so a model can look accurate during normal operation but fail to detect rare, critical faults. The main risk is that strong overall performance can hide poor results in the cases that matter most. When checking models for bias or imbalance, do not rely on one overall score. Look at how performance changes across equipment types, load ranges, and operating conditions. A model may work well in common situations but fail on rare defects or unusual energy use patterns. These edge cases matter in engineering because biased models can give unsafe recommendations when conditions differ from the familiar data they learned from. Managing bias and imbalance means understanding a model's limits and adding safeguards, not expecting perfection. Engineers should check performance across subgroups, compare common and rare errors, and make sure the data matches the real environment. When rare failures are underrepresented, targeted data collection or better evaluation metrics may be needed. Clear communication, engineering judgment, and human oversight help keep model recommendations fair and reliable in practice. Python code, bias and imbalance. Bias and class imbalance can make a model look more accurate than it really is by hiding rare failures. Checking performance across different groups helps reveal these risks. We begin by importing 3 key Python libraries for data work. NumPy for efficient numerical operations, Pandas for organizing and analyzing structured data, and Matplotlib's plotting tools for creating visualizations. Together, these libraries provide the foundation for computing, managing data, and displaying results clearly. We create reproducible synthetic maintenance data by using a NumPy random number generator with a fixed seed of 42. The dataset includes 180 normal points and 20 fault points, reflecting a realistic case where faults are much less common than normal operation. We simulate vibration measurements for normal and faulty machine conditions. Normal data is generated around 2 millimeters per second with lower variation, while fault data is generated around 4.2 with higher variation. These two sets are then combined into one complete vibration dataset for analysis. The setup defines the true condition labels using 0 for normal operation and 1 for faults. It also assigns each data point to one of 2 machine groups, pump A or pump B. A vibration threshold of 3.6 is then set for later fault prediction. We predict machine faults with a simple threshold rule. If vibration is above the set limit, the machine is labeled as faulty. Otherwise, it is labeled normal. These predictions are stored as ones and zeros, then organized in a pandas data frame with the machine group, actual fault status, and predicted fault status. This structure makes it easy to compare the model's predictions with the real outcomes. The metrics function summarizes model performance from a data table. It counts the total predictions, the number of correct predictions, the total actual faults, and the faults correctly predicted. These values provide the basic counts needed to calculate accuracy and recall. The model's performance is summarized with three values: accuracy, recall, and the total number of faults. Accuracy shows how often predictions are correct overall, while recall shows how many actual faults the model successfully identifies. The recall calculation also guards against division by zero when there are no faults. We first use the metrics function on the full dataset to measure overall accuracy, recall, and the number of detected faults. Then we repeat the same evaluation separately for pump A and pump B by filtering the data for each group. Comparing these results shows whether the model performs consistently across machines or has differences in fault detection by subgroup. The output summarizes model performance by reporting overall accuracy and overall fault recall, both rounded to 2 decimal places. It also shows how many faults occur for pump A and pump B, then compares fault recall for each pump. Together, these results help evaluate how well the model detects faults and whether performance differs between the 2 machine groups. The process compares fault detection performance for pump A and pump B by plotting their recall values in a simple bar chart. Each pump is shown with a separate colored bar, making it easy to see whether one group detects faults better than the other. This visualization highlights any imbalance in recall between the 2 machine groups. The plot is formatted to make rare fault detection results easy to read. The vertical scale is set from 0 to just above 1. The y-axis is labeled as fault recall, and the title identifies the comparison by machine group. A lightly transparent horizontal grid helps compare recall values without cluttering the chart. The script ends by using the matplotlib show function to display the completed plot. The plot summarizes fault recall rates across machine groups, making it easier to see whether fault detection performance is balanced across subgroups. This script simulates vibration data for 2 pumps under normal and fault conditions, then uses a simple vibration threshold to predict faults. It reports overall accuracy and fault detection performance for each pump, focusing on recall as the measure of how many true faults are found. By comparing recall for pump A and pump B, it shows that performance can differ across subgroups. The main lesson is that data imbalance or bias can make a model appear effective overall, while still detecting faults unevenly between groups. Bias and drift. When a model is used in conditions different from where it was developed, bias and drift can reduce its reliability. Bias is a consistent error that favors some cases, while drift is a change in data or environment over time. In mechanical engineering, these often interact, such as when a maintenance model trained on new machines performs poorly on older machines or different settings. As conditions change, old biases may become stronger, and new ones may appear. Bias and drift occur when changing conditions leave parts of a model's original training context behind. A model may perform poorly after changes in equipment, lighting, or human behavior, such as in quality inspection or energy forecasting. The issue is not only reduced accuracy, but also uneven effects across different groups or settings. Recognizing this is important for managing the wider impact of deployed models. After deployment, models must be monitored for both overall performance and subgroup performance, because average error can hide failures in specific machines or user groups. Engineers should keep checking whether model assumptions still hold as conditions change. If bias or drift appears, they may need more data, retraining, or threshold adjustments. Treating models as part of a changing system helps keep decisions accurate and fair. Python code, bias and drift. Bias and drift can affect engineering models after deployment. This example uses simple built-in calculations to compare overall average errors with errors across subgroups. We import NumPy for numerical work and random number generation, pandas for managing and analyzing tabular data, and matplotlib's plotting tools to visualize data and results. We generate reproducible operating data by using NumPy's random number generator with a fixed seed of 7. We then set each group to have 40 data points, giving equal sample sizes for the newer and older machines. The simulation creates two machine age groups, newer machines with ages centered around 2 years and older machines with ages centered around 12 years. The generated ages are combined into one dataset, and matching labels mark each machine as new or old. This prepares the data so the two groups can be compared in later analysis. Vibration levels are simulated from each machine's age, starting with a base value and adding a small amount of random noise. The true risk is then calculated as increasing with both vibration level and machine age. In short, older machines and higher vibrations lead to higher modeled risk. We first identify the newer machines with a Boolean mask, then use only those machines to fit a linear model with NumPy's polyfit function. The model estimates the line relating vibration to true risk for this subset. Training only on newer machines intentionally introduces bias, which lets us study how that bias affects predictions when conditions change. We first estimate machine risk using the biased model's intercept and slope with the original vibration data. Then we simulate data drift by increasing vibration more for older machines than for newer ones, reflecting changing operating conditions. Reapplying the same model to the shifted data shows how predictions change and helps reveal the effects of bias and drift. We compare prediction errors before and after drift by subtracting the true risk values from the predicted risk values in each case. These signed errors show whether predictions are too high or too low. The results are then organized by machine group in a data table, making it easier to analyze and visualize how errors differ between new and old machines. We compare model accuracy before and after drift by calculating the mean absolute error for each period, which shows the average size of prediction errors regardless of direction. Then, the errors are grouped by machine age and averaged, with results rounded for readability. This makes it easier to see how drift affects performance overall, and how errors differ between new and old machines. We compare prediction accuracy before and after drift by reporting the mean absolute error for each period, giving a baseline and showing the drift's impact. We also report the mean signed error for each machine group to reveal differences between newer and older machines. A positive error means the model predicts higher risk than actually occurs, indicating overestimation bias. We use a bar chart to compare the mean signed error for new and old machine groups. This shows whether each group tends to have positive or negative errors, helping reveal changes in bias when operating data drifts. A zero reference line makes the direction of the error easy to interpret. This script shows how bias and data drift can reduce the accuracy of engineering models. It simulates vibration data from newer and older machines, trains a risk model only on newer machines, and then compares prediction errors before and after the vibration data shifts. The results show that drift increases errors overall, with the largest impact on older machines. A bar chart summarizes the signed errors for each group, making the change in bias after drift clear. Evidence-based recommendations. Model evidence. In engineering AI projects, model evidence explains why a model's recommendation makes sense in the real system, not just how accurate it is. A failure prediction should be tied to signals such as vibration or temperature, and a process recommendation should connect to outcomes like part quality or defect rates. Clear evidence helps stakeholders understand the prediction, the data behind it, and how it aligns with engineering principles, which is essential for decisions involving cost, safety, and reliability. Model evidence should combine several kinds of support because each answers a different question. Performance metrics show how well the model works, but their importance depends on the engineering task and the consequences of error. Error analysis reveals where the model performs well or poorly, while visual and feature evidence helps confirm that it is using meaningful inputs rather than irrelevant patterns. Model evidence connects analysis to action by showing when a model's results are reliable enough to support engineering decisions. Whether detecting air leaks, predicting heat exchanger fouling, or evaluating design alternatives, the model should be validated across relevant conditions and compared with trusted data or simulations. Clear reporting should explain the data sources, validation approach, main results, and practical implications, so the team can judge and improve the recommendation. Python code. Model evidence. Model evidence helps connect predictions to real engineering behavior. Small examples can demonstrate responsible recommendation logic using transparent calculations and plots. The script begins by importing key Python libraries for data work. NumPy supports efficient numerical operations and arrays. Pandas helps manage and analyze data with data frames, and Matplotlib PyPlot creates charts and graphs. Together, these tools prepare the script for data manipulation, analysis, and visualization. We create reproducible pump monitoring data by using a fixed random seed and generating a time series of hours from 1 to 40. This gives the simulation a consistent set of floating point time values each time it runs. Synthetic vibration data is created by modeling a steady increase over time and adding normally distributed random noise to mimic measurement variability. Temperature data is generated in a similar way, starting from a base of 68 degrees, rising gradually with time, and adding larger random fluctuations. Together, these steps produce realistic simulated evidence for later analysis. The maintenance risk score starts with a baseline of 12, then increases based on vibration and temperature. Vibration has a stronger effect, while temperature adds a smaller contribution. Random normal noise with mean 0 and standard deviation 3 is also added across the time range to simulate real-world measurement variation. We use pandas to create a data frame that organizes the data in one place. It begins with columns for hours and vibration, then adds a temperature column with its matching values. This combines the evidence into a compact table that is easier to analyze and work with. We add the calculated risk values as a new column in the data table, so the dataset contains all needed information for later analysis. Then we use an assertion to check that the table has 40 rows and 4 columns, confirming the data structure is correct before continuing. We prepare the data by separating the input features from the target. Vibration and temperature are converted into an array for the model inputs, while risk is converted into a separate array as the value to predict. This setup lets the linear model learn how vibration and temperature relate to risk. To prepare data for linear regression, we add an intercept column of ones, so the model can include a constant term and does not have to pass through the origin. This intercept is combined with the vibration and temperature features to form the design matrix used to find the best fitting coefficients. To solve a least squares problem without machine learning libraries, use NumPy's linear algebra tools to find the coefficients that best fit the design matrix to the target values. These coefficients define the optimal linear relationship in the data. Predicted risk scores are then found by multiplying the design matrix by the coefficients. To evaluate the model, we compare each predicted risk value with the actual target value to find the error. Then we take the average of the absolute errors, giving the mean absolute error. This tells us how far the predictions are from the true risk values on average, measured in risk points. We evaluate the model using root mean squared error, which shows the typical size of prediction errors. Then we flag cases with predicted risk scores of 85 or higher as high risk. Counting those flagged cases gives the total number of recommended inspections based on the model's predictions. The output gives decision makers a quick summary of the pump maintenance model. It reports key accuracy measures, including mean absolute error and root mean squared error, along with how vibration and temperature affect the predicted risk score. It also shows how many records are flagged for inspection because their predicted risk is high, helping stakeholders judge both model performance and maintenance needs. A new plotting canvas is created. Then a scatter plot compares measured maintenance risk with predicted risk. Each point represents one record, with actual risk on the horizontal axis and predicted risk on the vertical axis. The points are colored steel blue and labeled as records for the legend. To show perfect agreement on the plot, set the axis limits slightly beyond the range of the measured target values. Then draw a dashed diagonal line across those limits. This line marks where predictions would exactly match the measurements, giving a clear benchmark for comparison. The plot is labeled to compare measured maintenance risk on the x-axis with predicted maintenance risk on the y-axis. Its title explains that the visualization shows model evidence by comparing predicted and measured risk, and a legend is added to make the plot elements easier to interpret. The code uses matplotlib's tight layout function to adjust the plot so labels, titles, and other elements do not overlap. It then uses the show function to display the plot, letting users compare predicted and measured risk values to assess the model's performance. This script simulates pump monitoring data by generating vibration and temperature readings, then uses them to estimate maintenance risk. It fits a simple linear model to predict risk and checks accuracy with common error measures. The script also counts high-risk records to guide inspection decisions and compares measured and predicted risk in a plot to show how closely the model matches the data. Evidence strength. In mechanical engineering, evidence strength means showing that evidence is reliable enough to support decisions such as design changes or maintenance plans. Strong evidence comes from consistent, relevant, and repeatable results across sources, like validation performance and error analysis. A model's metrics matter, but the main question is whether the evidence is robust enough to justify the action. Evidence strength should be described as promising, decision-ready, or insufficient. Promising evidence suggests a model may work, but only in limited settings. while decision-ready evidence shows reliable performance across varied conditions. The key is to explain the scope of testing, how serious the errors are, and what the consequences would be if people rely on the model's output. When presenting AI recommendations in engineering, match the strength of the claim to the maturity of the evidence. Because decisions can affect cost, safety, and compliance, recommendations should state what the data supports and how confident we are, without implying certainty. If evidence is limited, such as missing failure cases or untested operating conditions, a pilot program or further validation may be more appropriate than immediate adoption. Python code, evidence strength. Evidence strength helps connect metrics to practical engineering decisions. In this example, recommendation readiness is scored through simple checks using small synthetic compressor data to keep the results easy to understand. This setup imports key Python libraries for data work. NumPy supports efficient numerical calculations with arrays. Pandas is available for data manipulation, and Matplotlib's plotting tools enable visualizations. Together, these imports prepare the script for analysis and visualization tasks. A fixed random seed is used so the generated results are repeatable each time the code runs. The script then creates 80 simulated compressor operating hour values, randomly spread between 100 and 2,000 hours, to support later calculations. We simulate compressor condition data by modeling temperature and vibration as gradually increasing with operating hours, while adding random noise to make the measurements more realistic. Temperature uses larger variation, while vibration uses smaller variation. These two measurements are then combined into a single risk score, with temperature given a smaller weight and vibration a larger weight to assess the compressor's condition. A simple risk model predicts risk by combining temperature and vibration measurements with fixed weights, then adding a small constant. To evaluate the model, we compare each prediction with the actual risk value. Taking the absolute error shows how large each prediction mistake is, regardless of whether the model overestimated or underestimated the risk. The code first verifies that the error and temperature data have the expected matching length. It then identifies high-risk cases where the actual risk is above the 80th percentile. Finally, it averages the absolute errors for those cases to measure performance specifically in the most critical scenarios. The model is evaluated using 4 checks: overall accuracy, coverage, plausibility, and stability. Accuracy comes from the average absolute difference between predicted and actual risk, while coverage shows the share of cases marked critical. Plausibility is confirmed when the prediction coefficients are positive, and stability is checked by ensuring errors stay low for critical cases. The code counts how many validation checks pass, including error level, coverage, parameter plausibility, and critical error stability. If all 4 checks pass, the evidence is treated as decision-ready. Otherwise, it is considered promising. The recommendation then follows from that rating. Pilot automated inspections when the evidence is decision-ready, or collect more data when it is not. The output summarizes model performance by reporting overall mean absolute error, error on the highest risk cases, and how many of 4 evidence checks passed. It then labels the evidence strength to indicate readiness for decision-making and gives a recommendation, such as piloting automated inspections or collecting more data. This plot compares actual compressor risk scores with predicted scores using a scatter plot. A diagonal reference line shows where predictions would exactly match the actual values, making errors easy to spot. Clear access labels, a title, and a light grid helps stakeholders quickly judge how well the model's predictions align with the evidence. This script tests whether a compressor risk recommendation model is ready for use by generating synthetic temperature and vibration data, then comparing actual and predicted risk scores. It measures accuracy with mean absolute error and critical case error, and checks whether performance is plausible, stable, and reliable for high-risk cases. Based on these results, it labels the evidence as either decision-ready or promising, recommending automated inspection pilots only when the model passes enough checks. It also reports the key errors and shows a scatter plot so stakeholders can compare predicted and actual risk scores. Limitations and next steps. When using a model to guide engineering decisions, clearly state what it cannot prove and where it may fail. A model may work only under certain equipment, operating conditions, or phases of operation, so its limits must be understood before acting on its results. Communicating these limits helps distinguish a decision support tool from a fully validated strategy and makes the recommendations stronger, not weaker. When presenting limitations, connect each one to a practical action. Small or imbalanced datasets may require more targeted data collection, diverse conditions, or simulations to improve confidence in event detection. Complex models should be checked against simpler models and reviewed with domain experts to confirm they use meaningful signals. Risks like data drift should be handled through ongoing monitoring and revalidation, making limitations part of an active engineering plan. Project recommendations should match the risk, cost, and impact of the decision. Low-risk uses, such as routine HVAC checks, may allow some uncertainty, while critical tasks like pressure vessel integrity require strong validation and oversight. Recommendations should state whether a model is ready to use, needs more testing, or should be revised, and identify the reviewers and data needed to build confidence. A limited trial with performance monitoring can help balance AI's value with engineering's need for evidence-based decisions. Python code, limitations, and next steps. Responsible engineering recommendations should be guided by evidence. Limitations are most useful when they lead to clear actions, and deployment readiness should be scored transparently. We import 3 core Python libraries for data work: NumPy for efficient numerical operations in arrays, Pandas for organizing and analyzing data with data frames, and Matplotlib's PyPlot module for creating plots and visualizations. The setup defines project aspects such as test coverage and explainability, then assigns each one 2 values, a support score and a risk level, both ranging from 0 to 1. These values provide a simple way to compare current evidence against potential risks when judging deployment readiness. First, confirm that the item, score, and risk lists all have the same length, so each item matches 1 score and 1 risk value. Then check that every score is between 0 and 1, ensuring the scores are valid probabilities for later analysis. To prioritize actions, first find each evidence gap by subtracting its score from 1, showing how much improvement is needed. Then multiply each gap by its related risk to create a priority score that reflects both need and potential impact. We use Pandas to organize the project evidence into a structured table with limitations, evidence scores, and priority scores. The table is then sorted so the highest priority items appear first. This highlights the most important evidence gaps, weighted by risk, so attention can be focused where it is needed most. The code recommends starting with a limited pilot instead of a full deployment, reflecting a cautious approach based on the available evidence. It then identifies the highest priority next steps by ranking evidence gaps according to risk. Finally, it presents the top 3 improvement areas with their priority scores, helping stakeholders focus resources where they are most needed. This creates a bar chart that turns plan limitations into next step priorities. The x-axis lists the limitations, while the y-axis shows their risk-weighted evidence gap scores. The chart uses clear labeling, readable rotated category names, and an adjusted layout, so the visualization is easy to interpret. This script assesses whether a project is ready for deployment by comparing evidence gaps with the risks tied to each limitation. It ranks the highest risk-weighted gaps to identify the most urgent improvements. The result recommends a limited pilot instead of full deployment, with a chart used to highlight the top priority areas for stakeholders. In this lecture, you learned to interpret model behavior using coefficients, rules, errors, plots, and feature sensitivity checks. Evaluate practical limitations such as overfitting, imbalance bias, data drift, and explainability. And communicate a complete mechanical engineering AI project with evidence-based recommendations. Congratulations on completing this course. Thank you for your attention. See you all in the next lecture.